Hey everyone, welcome back to Console. Don't forget to subscribe and hit the little bell so you're notified on every new Console episode, which happens every week. We're going to take a brief detour away from programming languages because I'm getting sick of doing compilers and programming language content. I found a blog post titled Quantum Computing for the Very Curious, and so I wanted to dabble in some quantum computing for a little bit. Turns out I'm not as interested in quantum computing as I thought I was, but it was still useful to go investigate it, to learn that myself. One thing I found reading this post was there's kind of a lot of bad information out there related to quantum computing. A lot of the things that I thought were true about the field were not that true actually after digging into the details. Seemed a little bit like blockchain. Like back when I was a blockchain consultant, there was a lot of information related to blockchain on the internet that was ranking high on search engines and things like that. There was just total garbage content. There was a lot of misconceptions, a lot of misinformation out there, and it seems to me at least that quantum computing kind of has the same problem. I think almost anything that has major hype behind it is going to have a bunch of people trying to profit off of that content, which means you're going to get a lot of BS, clickbait kind of stuff, ranking highly in searches for that particular topic. Anyway, like I said, it was kind of hard for me to get through this content, but it felt like after I had started it, I flagged it as something possibly interesting to go over. I felt I needed to get through it for sure and do a video about it. One kind of caution I'm going to give you before we start is this stuff is pretty advanced. It involves a lot of linear algebra and it involves a lot of circuits. So both of those things are things you kind of learn as a computer science student. They make you learn linear algebra, and in my case I did like a dual major between electrical engineering and computer science, and so I took a circuits class. So a lot of this stuff is basically what my summary of quantum computing is. They took circuits, classic circuits, which is just zeros and ones, right? Which is how computers are built. They're just a bunch of zeros and ones going into gates, and those gates enact various operations on sets of bits. And then we take that and we turn them into bytes. We talk about bytes, and then we blow the idea of the bits up and the gates into like larger constructs. Effectively, is how circuits work. They've taken the same approach for quantum computing and then applied linear algebra to it. Not only linear algebra, but complex variables inside the linear algebra. So that's why quantum computing is often hard to wrap your head around, because circuits are already kind of a bit of a confusing topic, particularly if you're not an electrical engineering student or something like that. And then you start adding linear algebra into the mix and complex variables into the mix, and it leads to a lot of confusion. So anyway, I just wanted to get that out of the way before we get started. With that out of the way, let's get started. Okay, this is the post. It's, like I said, titled Quantum Computing for the Very Curious. It's a series of a bunch of different posts. This one just happens to be like the for beginners kind of thing. And if there's more interest after I post this video for me to dive into more quantum related content, I'll go through the rest of them, right? You can see below there's like a how search algorithm works and all this other things. Quantum Country is the name of the website that's producing all this content, and I think they might be defunct now. I did a little digging on one of the authors, and he hasn't uploaded anything to YouTube in quite a while, so I don't know how well maintained this stuff is. One thing I noticed about the format, like kind of confused me when I first opened it, is you got this thing on the right side, this like weird little timeline looking thing, and what that is they're teaching you quantum computing, but at the same time they're trying to apply like a new strategy or a new bit of research that's correlated with learning. And so what they've done is they're going to ask you questions throughout the reading of the essays, and then they're going to send you a reminder if you sign up for it, which I didn't sign up for it. But if you do sign up for it, they're going to send you those questions periodically. And you can see here there's like a 5-day 2 weeks, 1 month, something like that, exponentially farther and farther out of in time, they're going to send you questions related to what you've read. And the claim in the essay is that this is going to help you learn better and help you remember the content that you've read, right? So what they're trying to do is kind of push for this idea of like everybody doing this sort of idea when they're writing essays, right? So like if I'm reading a magazine, right? We don't read as many magazines nowadays as we used to. Most of the content we read on websites, right? And so now with this, since we're all moving to digital, you can start applying different ideas to the way you're producing the content, right? And in this case, they're trying this new idea where basically they're going to ask you these questions to refresh your memory so that you maintain the information that you read for a longer period of time, or hopefully indefinitely, right? So that's what that is. It was a little confusing when I first opened it, but there's also like the navigation on that bar is a little confusing as well. This is actually the first post, and then there's subsets, part 1, 2, and 3 of this post. And we're only going to go through 1 and 2 for this video, and then we'll go over 3 in the third video, because 3 is like really the meaty stuff here. So right now what they're doing is they're motivating the idea of, or they're giving you a historical background in computing effectively, and like where the idea of the computer came from, right? Turing is famously well credited with coming up with the idea of the classical computer, and they're saying like he was motivated by this idea of like computability, basically, where Hilbert was postulating like is there or conjecturing like is there a way for us to find out if given a mathematical statement it's provable or not, right? So Turing was operating in those contexts when he effectively invented the idea of the computer and an algorithm where it was like, you know, you could just put some steps into a computer and get an answer, yes or no, this is provable. And you take that one step further, you could get an answer, yes or no, or whatever, for some inputs, right? So here he's talking about the idea came from like Turing was basically going like, what steps does a human take when they're computing something, right? They have some state of the problem in their brain, and maybe like 10 variables, and they're maintaining this state somewhere in their brain, and then they're writing things down on their piece of paper about the state that they're aware of, and then they do steps on those variables on the paper, and while still maintaining a new state, let's say a prime, right? And so on and so on and so on. And the idea was like, well, can we take that and just apply, like, make a machine do that, or allow a machine to do that, right? Rather than a human doing that. So that's kind of where the idea of the computer came from. And obviously, this is a post about quantum computing, right? So you can kind of see where we're heading here. Is like they're giving you a background of like, this is where classical computers came from, but you know, what about quantum computers, for example? So what they're saying here is effectively, so Deutsch was a quantum physicist, basically, and against the backdrop of like Turing's classical computational model, Deutsch was kind of thinking, is there a way of modeling the actual state of the universe, right? Because the problem with Turing machines is they're not very good at modeling quantum mechanics, right? This is like an inherent flaw in Turing machines, and why why we're looking to machine learning and things like that as an answer to certain questions, because computers are very rigid in some sense, right? Classical computers are very rigid in some sense. And so what we're trying to do here is, or what Deutsch is proposing is like, can we try a different method of computation, one that lends itself to modeling quantum mechanics a little bit better, right? And so that's where this idea of the quantum computer came from, right? Effectively, and where the idea of the qubit and all these other things that we're going to be discussing throughout the length of this essay. But they want to motivate that and give you a background and all this other stuff. I kept saying it took me a while to get through this essay. Like I had to do it in a bunch of chunks, and I think that's maybe part of the reason why I've said in previous console episodes that I prefer shorter blog posts, because they get straight to the point of what they're trying to convey here. And in this case, it was the writing was kind of academic. It was very long form, right? Took like, in order to understand quantum computing, I don't need to know the history of like Turing. These are things I'm already familiar with as a computer scientist. You may not be, but I am. And I just want to see what's going on in quantum computing right now. I don't need all this extra stuff, but I had to read it to get down to the nitty-gritty. So right here is where they're talking about kind of the background you'll need to know. I mentioned this in the introduction to the video. Like you need to have an understanding of AND gates, OR gates, NOT gates, and you also have to have an understanding of linear algebra to get through this. I'm not going to teach those things in this video. I'm not going to have any backgrounds in that. So if you don't know that stuff, you probably are not going to get much out of this video, frankly. So this is like beginning part 1, right? So we had all the overview of Turing and like motivation behind the quantum computer and all this other stuff. Now we're going to actually start talking about like what constitutes a quantum computer, right? And obviously in regular computers we have bits. I already talked about zeros and ones, all those other things, gates acting on those bits. We have the same thing here, right? They're basically talking about the qubit. Which is effectively, you can think of a vector, a 1, 0, 0, 1 vector, basically. If you only knew how much editing I just did to get to this state of the page. There's just so much content in this essay that it's more to do with that research-based learning thing. They put way too much of that content in this particular essay. Right here, they're finally getting back to the qubits, though, and what they're doing is they're giving you, effectively, most of this first part of the essay is giving you terminology, right? So they're talking about this computational basis state, which is a 1-0 vector. A couple other things they talk about is ket, which is like another name for the vector, effectively. It's just a bunch of terminology at this point. So here they're giving a more mathy explanation of these vectors, right? They defined those in the previous section. And now, if you're familiar with vectors, right, from linear algebra, you know you can multiply them by a magnitude of some kind, right? And that points you out into some particular space. What they'll mention below is like, this is just like regular space, right? But you can also do it into complex space as well, right? Which is the whole point of this whole concept of qubits, is you can do these vector multiplications and of magnitudes using both, real and complex variables, right? One thing particularly to note here is that the magnitude of every vector of a qubit has to sum to 1, right? And we'll talk about why that is later towards the end of the essay. I kind of wish they would have pointed that out right now, rather than having to make you read through all this wall of text to understand why, but they point it out here, so I figured I'd mention it as well. So anyway, to conclude this section, right, it's just standard linear algebra. As you would expect, you can multiply a magnitude into these vectors, but these vectors can also take complex variables, right? So you can project into regular space and complex space. Simple as that. I misspoke a little bit earlier when I said like the sum of the vectors has to sum to 1, right? What I meant to say is like the amplitude, right? The magnitude. The sums of the squares have to equal 1, right? It's obvious, like if you're familiar with linear algebra, you know what I'm talking about here, right? The magnitude of that vector has to sum to 1, but it's been a while since I've talked linear algebra, right? So I forgot like what exactly the terminology for that is. I just wanted to make sure and be very clear about what I meant here. You can see he's pointing all this out here and giving you a graphical representation of what they're trying to say. Again, this will make a lot more sense later on in the essay. Okay, so we've kind of talked briefly, like a very basic introduction to like the linear algebra, right, the math aspect of quantum computing. And now we're gonna, as I said in the introduction, right, it's like they took linear algebra and applied it to gates, right? And that's basically what we're doing here. We're now going to start talking about the logic gate aspect of quantum computing. Now that we've kind of, briefly went over the linear algebra, there's a lot more linear algebra later on in the video, but at this point we can start transitioning into, the various gates that we can operate on those two vectors that we discussed earlier. So the first gate that they talk about is a NOT gate. It's pretty standard, like you would even probably discuss a NOT gate in like a introductory circuits class. The NOT gate does generally what you would expect to those vectors as well, right? It takes the one vector and turns it into a 0 vector, and the 0 vector and turns it into a 1 vector. Or I should be calling these kets, right? Because that's the terminology in quantum computing. But I mean, to me, it's just linear algebra. They're just vectors. So after discussing the NOT gate, they discuss what you would call the wire, right? Which is logically a simple thing, right? You're not doing anything to the vector, but what they're starting to head into is the fact that, you know, quantum mechanics doesn't behave the same way classical mechanics does, right? And so they're talking about the, you know, the famous things that keep getting discussed in quantum computing all the time, which is like, it's hard to measure. The way you're storing the qubit is usually using like some sort of atom or a photon or something like that, right? And depending on like what physical thing you're using to store the information of the qubit, it may be more or less difficult to measure, right? And so what they're saying is like, yeah, it's easy for you to just draw the line and say like that's a wire, a qubit wire, right? But to actually make that happen is like an almost insurmountable task, and it depends on like what medium you use to store your qubits and all these other things, right? So they're talking about all those things that are, you know, famously discussed in quantum computing and all the blogs and all the misinformation I was talking about before, right? You kind of have, after watching this video, you understand like why it's a big deal, is because those wires are actually like kind of their theoretical, and to actually do them in physics and real devices is a like non-trivial task. So right here, they're basically just talking about if you put two NOT gates together, what do you get? And in this case, it's obvious, right? You just get back out what you put in. It's the same as like a classical circuit, right? Two knots together. You knot a knot, and it's going to be, in this case, they're showing you a wire. It's logically equivalent to a wire. So the gates we've looked at up to this point, right? They're pretty basic. And they analogize quite nicely to the classical circuit, right? They do exactly what you would expect. If you can even call the wire a gate, right? It doesn't do anything, doesn't act on any of the vectors. But this Hadamard Gate is the first gate that's specific to quantum computing, right? Like you can't do the same style of gate in classical circuitry, right? So this one's actually the first interesting gate that we're going to talk about that's specific to quantum computing. You can kind of think of it, at least the way I took it. Someone can correct me if I'm, not thinking about this correctly, but it seemed to me like it was a kind of a rotation of the qubits that are passed to it, or the kets that are passed to it, right? It will rotate them in some way. But one thing they point out that's kind of interesting is if you apply this gate twice in a row, you get the same qubit out that you put into it. And they'll discuss later like why that is the case and why and what property all quantum computing gates have to have such that is the case for this particular gate as well. But like I said, this one's more interesting. We're getting into like a more quantum specific ideas in this particular case. One thing they're pointing out here though is like there are no high level constructs in quantum computing right now. These are still like topics of research, and so that's why they're having to start the discussion with these low level quantum constructs, right? Which kind of sucks. Like I prefer to start at a high level and go into the details rather than starting at the details and going into the high level, but that's just the state of where we are in quantum computing right now. It is really like cutting edge research stuff, and so there's hardly any high level constructs. There are programming languages, and we probably will go into some of those in the future videos. We'll talk about like quantum computing programming languages, but we have to start somewhere, right? And that's why I'm going over this right now. Okay, so this episode's getting very long. I did not expect it to get this long. So I might have to split this into 3 parts rather than 2, because this video is already like 20 minutes long. In the next one, we're going to talk about how to measure qubits and how to have one qubit act on another qubit. You can do things like that with these qubits. And then in the third video, I might make these together depending on how long the other video is. In the third video, we'll talk about general computation, right? Similar to like how current Turing machines, right? They take these circuits and build them up together until you have something you can do general computation with. We'll start talking about how to do the same thing in a quantum computer as well. So I'll see you in those next videos.